Okay, now we're going to do another probability problem. An LED light bulb has an exponentially distributed life expectancy with a mean time of 5,000 hours. What is the probability light bulb will last more than 4,000 hours, last more than 10,000 hours, and if it's already lasted 5,000 hours, what's its probability it will last an additional 4,000 hours or more from that point? We're going to compare this. What do you think? A fresh bulb lasting 4,000 hours or one that's 5,000 hours old lasting 9,000 or more so that it runs another 4,000 hours? First off, let's write the probability density function. F of x equals 1 over 5,000 e to the negative x over 5,000 as long as x is greater than or equal to 0. 0 elsewhere. I've already graphed it for you on the calculator. And as you can see, it's going down. This window ends at 10,000. It will go down towards 0 asymptotically forever. Lasts more than 4,000 hours. From our previous probability discussion, we know that that's an integral, and we go from our lower limit to our upper limit that we're asking. So 4,000 hours is my lower limit, and there's no specified upper limit. The bulb can last forever as far as we're concerned. So infinity of f of x dx. Now here's a point though. If this is going on out to infinity forever, coming down, we know that the entire area under this curve has to equal 1, since it's a probability density function. And if this is 4,000 hours, we're trying to find this area here. The whole thing is 1. So rather than integrating to infinity, which we could approximate, we could put in some large numbers and begin to convince ourselves we've got most of the value of interest. Why not go 0 to 4,000 and subtract that answer from 1? Because this plus this has to equal 1. So that's going to be our approach. 1 minus 0 to 4,000 of f of x dx. Very simple to do this on the calculator. We've already got it graphed. So I'm going to second calculate integral is number 7. Lower limit is 0. Upper limit is 4,000. It shades in what we're getting this area here, and the answer is 0.5506, and so on. So 1 minus 0.55, approximately 0.45 is my answer. More than 10,000 hours. Well, then we want to move this up to 10,000. We're looking for 10,000 to infinity. So by the same logic, it's going to be 1 minus the integral of 0 to 10,000 of f of x dx. One minus 0.865, so 0.135. So 15% of the time you get lucky, the bulb lasts more than 10,000 hours, considerably longer than its mean. Now look at this question here, D. Bulb has already lasted 5,000 hours. Was probably last more than 4,000 hours more than that. Now what's happening here, if we think about this, so here's 9,000 and here's 5,000. We know the bulb has lasted to here. We're given that. So what we're calculating is a probability x is greater than or equal to 9,000 given x is greater than or equal to 5,000. Conditional probability. So our world has changed. And our whole world that we're going to be looking at now, we can disregard this part. We're interested in only the bulbs that last 5,000 hours or more. So 5,000 to infinity of f of x dx. And of those, how many make it to 9,000 or more? Now once again, we're going to do these reverse. We'll do 1 minus the integral of 0 to 5,000. So if I do that real quick here with an integral, lower limit 0, upper limit 5,000. For some reason it keeps the old shading on this calculator, which I'm not real thrilled about, but this is going to be 1 minus 0.632. And on top, we repeat, lower limit 0, upper limit 9,000. And I'll have 1 minus 0.834. So let's calculate these. 1 minus 0.632. And there's something wrong there. Wrong minus. We get 0.368 on the bottom. And on top I have 1 minus 0.834 for 0.166. So divide that answer by 0.368 and I get 0.45. Both have 1 actually. The same answer that I got in the problem asking would it last more than 4,000 hours. So we're seeing an interesting property of the exponential distribution here. It's memoryless. What that means is it doesn't care what the bulb has done. The probability of lasting 4,000 hours more is the same whether you have a fresh bulb or one that's 5,000 hours old. Now this is an important concept because I see these exponentials used for problems that are not really probably going to be exponentially distributed. For example, life expectancy. The probability of a 20-year-old college-age student, for example, living another 30 years is certainly different than the probability of a 90-year-old retiree. Somebody 90 to 120, that's a far less likelihood. Even if you've lived to 90, your odds of making it 30 more years is very different than someone who's much younger. So I've seen applied problems done in books occasionally with life expectancy, which would make no sense. Wrong distribution. Different processes are at play. So whether or not something like an LED light bulb would truly be exponentially distributed would be an open question we'd have to look into further. But we have seen how to use it, how to calculate it, and how to do them quickly on the calculator when we know something or we're given something is exponentially distributed. Thank you for watching this video.